Hello everybody. So in this video I want to introduce the idea of isotopes and also say a little bit more about atomic mass units. And I'm going to make use of this very nice table from a textbook in mineralogy by Klein and Dutrow, where they list the masses of the proton and the neutron and electron. And you can see earlier we talked about atomic mass units, or AMU, and we said that for protons and neutrons, they both had values of about 1. Well, it's not exactly 1. And you see they're a little bit different. The neutron has an atomic mass unit of 1.0086, whereas the proton is a little bit less, 1.007. And then here's the electron, much, much smaller than either the proton or neutron. And in calculating atomic weights, the electrons are usually neglected. So the protons, they're about 1 in terms of atomic mass units, but not exactly so. So how does that come into play? Well, let's take a detour and take a look at isotopes. We're going to look at isotopes of iron because these are pretty important in geology. So iron is any element that has 26 protons in its nucleus. So if you remember the Bohr model of the atom, we have a nucleus, and then there are a bunch of protons and neutrons that exist in that nucleus. Well, if the sum of those protons is equal, let's use this fancy Greek terminology, the sigma. So if the sum is equal to 26 for the numbers of protons, then you have to have iron. It can't be anything else. So the number of protons defines the kind of element that we have. On the other hand, if we have some number of neutrons here, it'll change the weight. So here are some number of neutrons. That could change the weight of an element, but it's not really going to have any impact on the kind of element. It has zero impact on the kind of element. So the number of protons tell you what kind of element you have. Well, for the case of iron, one of the most common isotopes has 30 neutrons. And so if we have 30 neutrons in the nucleus, then we would have a total atomic mass of 56. So 30 neutrons plus 26 protons would give us 56. Now notice here in writing this out, we're just using the simplification that the atomic mass unit is just 1. But if you go into something like PubChem, that's a pretty interesting website to investigate in your spare time, you'll see that the reported weight for atomic number 26, isotope 56, actually has this weight, 55.934936. This has nothing to do with natural abundances of iron. This is the measured weight of iron 56. It's not exactly 56. Notice that it's a little bit less than what we would get by adding protons and neutrons. In fact, this number is even a little bit low if we take these numbers at face value because they're both greater than 1. So how do we get something that is less than 1? And the reason why is very simple. When we start binding protons and neutrons together in the nucleus, we are taking some of that mass and we are converting it to energy. And that energy goes into the so-called binding energy, the nuclear binding energy that holds the nucleus together. And the amount of energy that is related to the amount of mass would be, according to this equation, the most famous equation probably of all time, E equals mc squared by Einstein, where notice that c here is the speed of light. Now the speed of light is very, very fast, about 300,000 kilometers per second. We're going to take that very fast speed and we're going to square it, so we get an even bigger number. So you take a mass, even a very small mass, we're going to multiply it by a very, very large number and we get huge amounts of energy. And that energy is the binding energy of the nucleus here. So large amounts of energy mean that force is very, very strong. It is probably the single most powerful known force in all of nature. The nuclear binding force is greater than the gravitational force, or much greater than the forces of electronic attraction, etc. And so that's why we get this difference here. Iron 56 is lighter because the protons and neutrons have lost some of their mass. They no longer have these values, and they've given it up to form this nuclear binding energy.